Hello students, in this video we will discuss very important topics: enthalpy, heat capacities, Cp and Cv, and relation between two heat capacities Cp and Cv of a system or a gas, that is Cp minus Cv is equal to capital R. In thermochemistry for BSc Part 1 chemistry courses, and in thermodynamics for class 11 chemistry in लेक्चर नंबर 2। इस वीडियो में हम लोग बीएससी पार्ट 1 केमिस्ट्री कोर्सेज के लिए एंड 11th केमिस्ट्री के लिए भी वेरी इंपॉर्टेंट टॉपिक्स थर्मोडायनामिक्स एंड थर्मोकेमिस्ट्री में डिस्कस करेंगे। इंथैल्पी, हीट कैपेसिटीज Cp and Cv, and relation between Cp and Cv, that is Cp minus Cv is equal to कैपिटल R को एस्टेब्लिश करेंगे। फर्स्ट ऑफ ऑल वी हैव टू डिस्कस इंथैल्पी। इंथैल्पी इज ए स्टेट फंक्शन, that is enthalpy of a system depends on its initial state and final state. Enthalpy is an extensive property of a system. Enthalpy is path independent. Enthalpy is denoted by the symbol capital H. Mathematically, enthalpy is defined as the sum of internal energy, say capital U, plus product of pressure and volume of the system. That is H equals to, H is the, capital H is the symbol of enthalpy, and it is equal to internal energy of the system. Say it is capital U. Internal energy of a system is denoted by the symbol capital U or capital E. So it is U plus product of pressure multiplied by volume. That is enthalpy of a system, capital H equals to capital U plus Pv. Suppose it is equation number 1. If the state change of a system is carried out at constant pressure, then according to the first law of thermodynamics, in terms of change in internal energy, it can be expressed as delta U equals to Q is the amount of heat minus W, where W is the work done by the system. If the change of a state is performed at constant pressure P, then volume of the system will change from its initial volume Vi to final volume Vf. Therefore, work done by the system is W equals to P multiplied by Vf minus Vi. So we can write delta U is equal to Q minus W is P multiplied by Vf minus Vi, where Vi is the initial volume of the system while Vf is the final volume of the system. अगर सिस्टम का स्टेट चेंज, दैट इज सिस्टम का स्टेट में जो चेंज होगा, चेंज ऑफ स्टेट, वह कांस्टेंट प्रेशर पर परफॉर्म किया जाए तो सिस्टम का वॉल्यूम, इनिशियल वॉल्यूम Vi से फाइनल वॉल्यूम Vf में चेंज होगा. तो वर्क डन बाय द सिस्टम in the mathematical expression of first law of thermodynamics, W can be expressed as constant pressure P multiplied by change in volume, that is Vf minus Vi. Delta U is the change in internal energy, that is final internal energy, say it is Uf minus initial internal energy, that is Ui, equals to, we can write it as Q minus PVF, Q minus PVF plus PVI. प्रेशर P को Vf से फर्स्ट टर्म से मल्टीप्लाई करने पर एंड नेक्स्ट सेकेंड टर्म से भी मल्टीप्लाई करने पर, ब्रैकेट को हटाने पर, ब्रैकेट को रिमूव करने पर, वी कैन राइट Uf minus Ui, that is change in internal energy of the system. Uf represents final internal energy of the system. Ui is the initial internal energy of the system, and it is equal to heat absorbed by the system Q minus work done is at constant pressure P multiplied by Vf minus Vi. So it is minus Vf PVF plus PVI. P से Vf and Vi को मल्टीप्लाई करने पर, ब्रैकेट हटाने के बाद, और वी कैन राइट Uf प्लस P इंटू Vf, Uf प्लस P इंटू Vf इक्वल्स टू Ui प्लस P इंटू Vi equals to Q, that is amount of heat at constant pressure. We can write Q as, at constant pressure we can write Q as Qp, heat absorbed by the system at constant pressure, because the change in the state of the system is carried out at constant pressure. So volume of the system changes from initial volume Vi to final volume Vf. So we can write it as Uf plus P into Vf माइनस पी वी एफ को अगर LHS में लाया जाए तो पॉजिटिव हो जाएगा, आई इक्वल टू यूआई को अगर RHS में ले जाया जाए तो माइनस यूआई प्लस यूआई हो जाएगा, प्लस पी वी आई एंड प्लस क्यूपी. और यूएफ प्लस पी वी एफ, वी नो दैट सम ऑफ इंटरनल एनर्जी यू प्लस प्रोडक्ट ऑफ प्रेशर एंड वॉल्यूम इज ए thermodynamic variable. It is a state variable or an extensive variable, and that a state variable is known as that quantity that thermodynamic quantity is known as enthalpy H. So UF plus PVF is HF, that is final enthalpy of the system. HF equals to UI plus PVI. UI is the initial internal energy of the system, plus P is the constant pressure, and Vi is the initial volume of the system. So the sum of UI plus PVI is the initial enthalpy of the system, and it is H, enthalpy denoted by the symbol H. So it is HI plus QP. QP is the heat absorbed by the system at constant pressure. So now we can write HF minus HI. HF minus HI, that is HF minus HI is the HF is the final enthalpy, HI is the initial enthalpy. Difference between final enthalpy minus initial enthalpy is delta H, that is change in enthalpy, equals to QP. HI को LHS में लाया गया. After HI is taken to if HI is taken in LHS, then we can write HF minus HI, that is change in enthalpy, and it can be represented by the symbol delta H. So HF minus HI equals to QP. QP is the heat absorbed by the system at constant pressure. So at constant pressure, if the heat is absorbed by the system at constant pressure, अगर सिस्टम द्वारा कांस्टेंट प्रेशर पर हीट को एब्जॉर्ब किया जाए, that is symbol is QP. QP is the amount of heat absorbed by the system at constant pressure, and it is equal to change in enthalpy of the system, that is delta H, that is final enthalpy HF minus initial enthalpy HI, and it is equation number 2. Change in enthalpy delta H is negative for the change in enthalpy delta H is negative for the exothermic reactions which evolve heat to the surrounding. So delta H is that is change in enthalpy is negative for the exothermic reactions. Write down change in enthalpy delta H is negative for the exothermic reactions. Exothermic reactions are those reactions in which heat evolve out from the system to the surrounding. Exothermic reaction वे रिएक्शंस हैं जिसमें सिस्टम से हीट सराउंडिंग में ट्रांसफर होता है. So delta H change in enthalpy is negative for the exothermic reactions, while change in enthalpy delta H is positive for the endothermic reactions. Endothermic reactions are those reactions in which heat is absorbed by the system from its surroundings. Endothermic reactions वे reactions हैं जिनमें सिस्टम सराउंडिंग से हीट को एब्जॉर्ब करता है. तो उस सिचुएशन में चेंज इन इंथैल्पी डेल्टा एच पॉजिटिव होगा इंडोथर्मिक रिएक्शंस के लिए, बट एक्सोथर्मिक रिएक्शंस के लिए डेल्टा एच निगेटिव होगा. सो डेल्टा एच इज पॉजिटिव फॉर द इंडोथर्मिक रिएक्शंस. After enthalpy, we have to discuss heat capacities Cp and Cp of a system or of a gas. But before it, we have to discuss heat capacity of a system or heat capacity of a substance. Heat capacity, which is denoted by the symbol C, and it is a constant of proportionality. If heat is absorbed by a system, then there is that resulted to increase in temperature of the system. अगर कोई सिस्टम हीट को एब्जॉर्ब करता है सराउंडिंग से तो उस सिस्टम का टेम्परेचर इंक्रीज कर जाता है. दैट इज हीट एब्जॉर्ब बाय द सिस्टम इज डायरेक्टली प्रोपोर्शनल टू its increase in temperature. That is, we can write it as mathematically, that is Q, amount of heat absorbed by a system, and it is directly proportional to its increase in temperature, that is delta T. Delta T is the difference between final temperature minus initial temperature, that is T2 minus T1 or TF minus TI. Or Q can be written as constant time, a constant C times delta T, that is rise in temperature or increase in temperature. Since Q varies as delta T, amount of heat absorbed by a system resulted to its rise or increase in temperature delta T. Therefore, we can write Q is equal to C, a constant of proportionality times delta T, a constant of proportionality C दे करके इसे इस रिलेशन को इक्वेशन के रूप में रिप्रेजेंट कर सकते हैं. Q is equal to C multiplied by delta T, and suppose it is equation number 1, and C, therefore C equals to Q upon delta T. That is, C is a constant, where C is a constant of proportionality, say it is equation 2. C is a constant of proportionality which is represented by amount of heat absorbed by the system, in this case upon rise in temperature delta T or change in temperature delta T. This ratio is known as heat capacity of a system, and it depends on the size of the system and also nature of the system. Heat capacity C. Units of heat capacity are joule per Kelvin in SI unit and calorie per degree centigrade in CGS unit. SI unit of heat capacity joule per Kelvin. SI unit of heat is joule and that of temperature is Kelvin, so it is joule per Kelvin. And CGS unit of heat capacity is calorie per degree centigrade. CGS unit of heat is calorie and CGS unit of temperature is degree centigrade. Heat capacity, if heat capacity of a substance is more or heat capacity of a substance is large, then there will be large amount of heat needed for a small temperature rise, a small temperature difference. For example, heat capacity of water is quite large, that is 4200 joule per kg per Kelvin, a specific heat capacity of water is. That means water requires large amount of heat for a small rise in temperature. A specific heat capacity is related to heat capacity of a substance or a system. That is, a specific heat capacity Cp equals to heat capacity per unit mass. And if heat capacity is expressed in mole, then it is called molar specific heat capacity. In that case, molar specific heat capacity is represented as the ratio of heat capacity per unit number of moles of the substance. That is molar heat capacity Cm. Molar heat capacity is denoted by the symbol Cm, and Cm is equal to C suffix में m होगा, is equal to heat capacity C upon number of moles of the of a substance or the system. For a gas, it is number of moles of the gas. So molar specific heat capacity of the system is represented as Cm equals to C upon mu, where mu is the number of moles of the system. And a specific heat capacity Cs, it is denoted by the symbol Cs, is equal to heat capacity per unit mass. So SI unit of a specific heat capacity is joule per kg per Kelvin, and CGS unit of a specific heat capacity is calorie per gram per degree centigrade. So write down a specific heat capacity of a system or of a substance. Cs equals to heat capacity per unit mass. Heat capacity upon heat capacity of the system or heat capacity of the substance upon mass of the system. That is, heat capacity is denoted by the symbol C and mass is denoted by the symbol M. C upon M, and it is a specific heat capacity. Now we have to discuss heat capacities Cp and Cv for a system. For a gas, if the system is gas, then there are two specific heat capacities. A specific heat capacity at constant pressure, it is denoted by the symbol Cp, and heat capacity or specific heat capacity of the gas at constant volume, which is denoted by the symbol Cp. While for solids and also for liquids, there is only one specific heat. But for gases, if the system is gas, there are two specific heat capacities. First, heat capacity at constant pressure, which is denoted by the symbol Cp, and the second, heat capacity of a gas at constant volume, which is denoted by the symbol Cp. In case of gases, there is large change in pressure and volume for very small rise in temperature, say 1 degree C temperature. So there are two specific heat capacities of a gas, that is Cp and Cv. But in case of solids and also for liquids, there is marginal change, very small change in its pressure and volume of a definite amount of a substance when its temperature is increased by a small amount, say 1 degree C or 1 Kelvin. Solids and liquid के केस में अगर 1 kg मास का सब्सटेंस है और ए डिफिनिट अमाउंट ऑफ ए सब्सटेंस है, तो उसका टेम्परेचर 1 डिग्री सी और 1 केल्विन से अगर रेज किया जाता है, तो उसके प्रेशर एंड वॉल्यूम में बहुत ही मार्जिनल चेंज होता है. देयर इज मार्जिनल चेंज इन द प्रेशर एंड वॉल्यूम ऑफ ए सॉलिड और ए लिक्विड of a say 1 kg or a definite amount of a solid or a liquid. If its temperature is increased through 1 degree C or 1 K, there is marginal change, very small change in its pressure and volume. That is for a solid or a liquid. So there is only one specific heat or a specific heat capacity or heat capacity of a solid or a liquid. But in case of gases, there is very significant change in its pressure and volume if its temperature is raised or increased through 1 degree C or 1 Kelvin. तो अगर किसी गैस के एक सर्टेन अमाउंट का, और सपोज किया जाए 1 kg मास किसी गैस का है और उसका टेम्परेचर 1 डिग्री सी और 1 केल्विन से अगर रेज किया जाता है, इंक्रीज किया जाता है, तो उस गैस के प्रेशर एंड टेम्परेचर, प्रेशर एंड वॉल्यूम में सिग्निफिकेंट चेंज आएगा, लार्ज चेंज आएगा, जिसे इग्नोर नहीं किया जा सकता है. सॉलिड्स एंड लिक्विड्स के केसेस में प्रेशर एंड वॉल्यूम में जो चेंज होता है वह मार्जिनल होता है, बहुत स्लाइट होता है, तो उसको तो इग्नोर हम कर सकते हैं. लेकिन इन केस ऑफ गैसेस, चेंज इन प्रेशर एंड चेंज इन वॉल्यूम of a gas, if a certain amount of gas is heated to very small temperature, say 1 degree C or 1 Kelvin, then there is a large significant change in the pressure and volume of the gas, which cannot be ignored. So there are two specific heats or two heat capacities of gases, Cp and Cv. So we can define now a heat capacity of a system, that is gas at constant pressure, and it is represented as Cp, that is heat capacity of a system. Gas is represented as Cp is equal to change in enthalpy of the system per unit increase in temperature, that is delta H upon delta T at constant pressure. प्रेशर को कांस्टेंट रखना होगा, तो पर यूनिट सिस्टम के गैस के टेम्परेचर में चेंज के लिए, चेंज होने पर उस सिस्टम के इंथैल्पी में जितना चेंज होगा उसको कहा जाएगा a specific heat capacity of the system, that is gas at constant pressure, and it is represented by Cp equals to delta H, that is change in enthalpy, that is del H, sorry, which is partial differentiation. It is not delta, it is del H. Del H upon del T, where del T is a small change in, partial change in temperature of the system. Del H upon del T at constant pressure, and it is Cp. It is Cp, a specific heat capacity of a system, that is of a gas at constant pressure. Let it is equation number 1. It is heat capacity of a system of a gas at constant pressure. Cp is equal to del H upon del T at constant pressure. While a specific heat capacity of a system gas at constant volume is defined as change in internal energy of the system per unit increase और राइज इन टेम्परेचर. किसी सिस्टम का गैस का टेम्परेचर 1 डिग्री सी और 1 केल्विन से राइज करने पर इंक्रीज करने पर उसके इंटरनल एनर्जी में जो चेंज होता है उसे एट कांस्टेंट वॉल्यूम, गैस सिस्टम के गैस के वॉल्यूम को कांस्टेंट रखकर तो उसे स्पेसिफिक हीट कैपेसिटी एट कांस्टेंट वॉल्यूम कहा जाता है और उसे सीवी संकेत से डिनोट किया जाता है. दैट इज स्पेसिफिक हीट कैपेसिटी ऑफ ए गैस और of a system at constant volume is represented by Cv equals to del U, which is change in internal energy per unit increase in temperature, that is del U upon del T at constant volume. So Cv equals to del U, U is the internal energy of the system, del U upon del T at constant volume. Constant volume लिखने का तरीका है, मेथड है कि ब्रैकेट दे करके सफिक्स में सिंबल भी को लिखा जाए एट कांस्टेंट वॉल्यूम, और एंड सीपी के केस में सीपी इज इक्वल टू डेल एच अपॉन डेल टी एट कांस्टेंट प्रेशर. तो यहाँ पर भी ब्रैकेट दे डेल एच अपॉन डेल्टा टी को ब्रैकेट में रखकर सफिक्स में नीचे प्रेशर को का सिंबल पी लिखा जाता है. तो यह एट कांस्टेंट प्रेशर हो गया डेल एच अपॉन डेल टी एट कांस्टेंट प्रेशर सीपी, एंड स्पेसिफिक heat capacity of a gas at constant volume Cv equals to del U upon del T at constant volume. For a specific heat capacity we can write Cp equals to 1 by m into delta H upon delta T at constant pressure, and a specific heat capacity of the system of the gas at constant volume can be written as Cv equal to 1 by m in terms of mass, or in case of number of moles we can write 1 by mu del U upon del T at constant volume. But in terms of mass it can be written as a specific heat capacity of a gas can be written as Cv is equal to 1 by m del U upon del T at constant volume. But here Cp and Cv are heat capacity of a system or a gas at constant pressure, that is Cp equals to del H upon del T at constant pressure P, while heat capacity of the system gas at constant volume is Cv equal to del U upon del T at constant volume V. Thus we have discussed heat capacities of a system or a gas. Now we have to obtain a very important relation between two specific heats of the system or a gas, that is Cp minus Cv is equal to capital R, which is also known as Mayer's formula. Now we have to derive this formula, that is relation between Cp and Cv, which is Cp minus Cv equals to capital R, where capital R is gas constant, whose value is capital R is equal to 8.31 joule per kg per Kelvin. Value of R capital R is 8.31 joule per mole per Kelvin in terms of number of moles of the gas. So R capital R is known as gas constant. Now we have to establish relation between two specific relation between two heat capacities of the system, that is of a gas, that is Cp minus Cv is equal to R. That is Mayer's formula. That is to derive Cp minus Cv equals to capital R. This relation, very important derivation. We know that heat absorbed by the system, heat absorbed by a system, that is gas at constant pressure, is Qp, amount of heat absorbed by the system or a gas at constant pressure, Qp equals to, we can write it as Cp, heat capacity at constant pressure multiplied by change in temperature, delta T. And Qp is equal to, we have already established this relation in this video in the topic enthalpy, that is Cp multiplied by Qp equals to Cp multiplied by delta T, and Qp equals to delta H. We have already obtained, that is change in enthalpy, delta H. Say it is equation number 1. And heat absorbed by the system or heat absorbed by the gas at constant volume, we can write it as that amount of heat absorbed by the system at constant volume as Qb equals to Cv multiplied by delta T, and it is equal to change in internal energy of the system, that is delta U. It is delta U. Say it is equation number 2. Now we know the relation between enthalpy of a system, its internal energy, enthalpy capital H, symbol of enthalpy is capital H, internal energy capital U, and pressure and volume of the system. Since enthalpy capital H is enthalpy capital H of a system is expressed as the sum of internal energy plus product of pressure and volume. So we have enthalpy of a system is H is equal to capital U plus P multiplied by V. This is enthalpy of the system. Enthalpy of a system. Suppose it is equation number 3. Now for change in enthalpy of the system, we can write delta H equals to delta U plus delta P into V, or delta H equals to delta U plus delta RT. From the ideal gas equation, PV is equal to RT. So in place of PV, we can write capital R into capital T, where R, capital R is gas constant. So PV is replaced by capital RT. Since capital R, which is known as gas constant, is a universal constant, so we can write this relation as delta H, that is change in enthalpy, equals to delta U, that is change in internal energy, plus capital R. Since capital R gas constant is a constant, it is a universal constant, so it is capital R multiplied by change in temperature, delta T. Or delta H is what? Delta H is given by Cp into delta T, that is heat absorbed by the system at constant pressure P, which is denoted by the symbol Qp. So Qp is equal to delta H. So in place of delta H, in LHS of this equation, say it is equation number 4. So in equation 4, in LHS of equation 4, in place of delta H, we can write Cp into delta T. So it is Cp multiplied by delta T equals to now delta U. First term of RHS is delta U, that is change in internal energy or increase in internal energy, and delta U is equal to Cv into delta T, that is amount of heat absorbed by the system at constant volume, which is denoted by the symbol Qv. So Qv equals to Cv into delta T, and it is equal to delta U, that is increase in or change in internal energy. So in place of internal energy, change in internal energy delta U, we can write Cv into delta T in the first term of RHS of equation 4. So delta U is replaced by Cv into delta T plus capital R, gas constant into delta T. Delta T is change in temperature. Now we have written Cp into delta T equals to Cv into delta T plus R into delta T. Now taking first term of RHS of this equation, say it is equation 5 into LHS, we have Cp into delta T minus Cv into delta T. Cv into delta T को LHS में लाने पर we have Cp delta T minus Cv delta T. Delta T is common in both terms. So delta T can be taken out of the bracket. So it is Cp minus Cv under bracket multiplied by delta T. Delta T is now common. It is taken out of the bracket. So Cp minus Cv under bracket multiplied by delta T equals to capital R into delta T. Delta T and delta T both sides will cancel out. So we have Cp minus Cv equals to capital R, and it is the final expression, and this is the required equation, that is required relation between difference in two heat capacities of the system, that is gas at constant pressure and at constant volume, that is Cp minus Cv is equal to capital R. And this is the relation between difference in two heat capacities of a gas or of a system, that is Cp minus Cv is equal to capital R. R is the gas constant or universal gas constant, whose value is to be calculated as 8.31 joule per mole per Kelvin. Now this video is completed. Thanks all of you for watching my YouTube channel, Physics Quantum Classes.